Yeah.
Where does the
The n comes from like the principal quantum numbers, so like going back to the Bohr model. But they also correspond with like the rows, right? But that's also why you have to label it. Like all the rows, but that's why you have to label it appropriately.
So I have a really quick question for you. For this lab, it says to just pick up article off of the thing. It doesn't have to be a journal, does it?
No, so like if you wanted to find another periodic table, yeah,
I
you
found a
can.
really cool one that's vertical.
Yeah, so then, yeah, just,
Okay, that
you
works.
can, yeah, and cite that.
An APA, of course, right?
Actually, I want to get y'all to use ACS at least, but APA is at least acceptable, but
ACS, I know what that is. I'm gonna have to look into
it's,
that.
yeah, it's just a format that chemistry journals use, but it's like pretty
Okay.
similar. It's just, kind of rearranges things, but,
Okay.
yeah.
I think this class is the same time next time, right?
Yeah.
So is calculus. I wish I switched with babies and I could go that way, which is gonna see. I can't. My she's a really good calculus teacher, and I would be surprised she would explain basic calculus concepts that I get. I wrote them better. Answer the question. I would not answer that. I guess I could have done that. I did the math. I think.
Last Friday, when you were texting me, I was doing
Oh my gosh,
It's okay.
and he texted me like at 10 o'clock. He was tomorrow. I was like, well, I got an app. Fridays are my homework days, but you need, I need a report on my vacation. Like, I need help. Okay.
I never poured them on food.
It's
It's not hot like
depending on how fast you pour it, it can dry out, and it's just the same. But the dude shows up on time with his concrete, and his concrete comes out. So for an hour, and you know how they work with like it's a piston, and it'll open and then close, and then that'll push it out, and it just like keeps switching as it's pumping concrete. I guess one of the pistons went out.
Yeah.
And I was like, oh yeah, I forgot to clean out the pump yesterday too, so I got to clean it first. Oh, this is the last, and then you.
No, there's left. Yeah. Yeah, it'll be done, yeah. Definitely last. Like, the students are just freaking me out, it's like, yeah, my other classes also asked me if we had lab night. And the syllabus, sorry.
Like 2 hours of work just so you can.
But yeah, that would work. Sorry, which one? Alyssa, okay. Yeah. Explain. And then Julie, you didn't take the quiz. Did you,
Other than
okay, yeah, I think we're gonna make that just the sooner the better. Yeah, that would be good, because I wanted to go over the quiz.
One or two. Are you doing? And then technical. No. I think mechanical, dynamic. I don't know. I had to fix it through from out of the loop. You're doing something in Mississippi, and you want to go for like 2 weeks. Right here. You getting some copies in here? Yeah, I think so.
All right. So let's get started on the review. So I have kind of like a few problems prepared, but we can always, of course, cover other things. I just kind of based it off of like what we haven't covered. But I did want to start off with, and I think I need to post the link still, so I'll do that once I get a little chance. But I annotated the periodic table, right? So how the midterm is going to work is you can use your periodic table for the multiple choice question, and then I'll also let you use your metric conversion little sheet that we handed out. And then I think that's really all you need. I'll probably provide like formulas. You could write formulas on the back of your periodic table, but my intention is to give you every formula that you would need on the exam. So just kind of, you know, can you plug it in, multiple choice question. So that will probably be like an hour, and then we'll take a 10-minute break or so, and then do the written portion, which will be open book and will just be written. So free response completely. And so my suggestion then to you is make sure that your periodic table is annotated properly, especially for electron configuration, which we'll talk about. Yeah, so constants, I'll give you constants like Planck's constants and electron mass. So I don't want anyone like trying to memorize anything weird or, right? We're just trying to understand our basics, use our periodic table. I mean, we have plenty to test on. Do we need to go over this? So I'm inclined to skip this kind of part for now, but if you have questions, you know, we can talk about it. You can kind of ask me individually. But again, this is how I suggest, right, setting ourselves up for success here. All right, let's try some practice problems. So we didn't do too many with chapter 4 with our wavelengths and energies. So let's try this first one here. So the eyes of a certain reptile pass a visual signal to the brain where visual receptors are struck by photons at a wavelength of 850 nanometers. If the total energy of 3.15 times 10 to the negative 14th joules is required to trip the signal, what is the minimum number of photons that must strike the receptor? Did I miss anybody? Everybody need to quiz back?
I didn't get one.
Oh. So how's this problem going? So what do we need to solve? What's our formula that relates energy and maybe wavelength? Yeah,
The frequency is the wavelength times the speed of light. And then 1 over wavelength is the solution of the equation.
so then what equation can we use to solve this? So you said some things, but where's energy and all that? So what about energy equals Planck's constant times speed of light over wavelength? And then, so the question is, well, what is this giving us, right? So we have to think about this. What is this saying? So when we're calculating this, right, and really when we calculate the energy of any transition, right, and what we're really saying is, okay, we're looking at one photon, right? So what it takes to just move one little electron. So you're just talking about, right, one photon here. So really when you're solving for this energy, right, this is the energy of one photon. And so that's what we need to solve first, right, is, okay, we have this wavelength. And so we need to figure out how much energy is in one individual packet, in one individual photon. And then, okay, then we'll be able to divide that and figure out how many photons we need.
Is H Planck's constant?
Yeah. Yeah, and so like I said, on the exam, on the front cover, I'll have all the constants and all that for you. So right now, you'll just have to refer to your notes. So
Do we have the equation?
yeah, so I'll provide all the relevant equations. So C is the speed of light. And then wavelength, don't forget to convert that to meters. Just punching it in to solve for energy. And then I'm just going to do kind of a lazy conversion. All right, so then we should get something like this. So do we all get about 2.34 times 10 to the negative 19 joules? I'll put here, right, of one photon then. All right, so then going back to the problem, well, it says that we have to receive a total energy of 3.15 times 10 to the negative 14 joules. So, right, thinking about how we can detect light. So there has to be some sort of threshold. You have to have enough energy. And so now we can just divide. So we have our energy total. So 3.15 times 10 to the negative 14 joules divided by the energy of one photon. Oops. Two virtual machines on there. And so dividing, so we should get something, so what is that? 1, 2, 3, 4, 5. So 1.35 times 10 to the 5th joules, or photons, sorry. 1, 2, So 1.35 times 10 to the fifth photons.
You converted nanometers to, yeah, nanometers to meters.
Yeah, so I just did that when I punched it in. So I just multiplied it by the factor, so times 10 to the ninth. I just didn't bother converting in the proper format. All right, so let's try another one. Oh, sorry. I'll try to show this bottom one. And so I think I had mentioned this kind of briefly in the lecture, but kind of look at our equation, and I can write out kind of our two relevant equations here. And then, so what is this asking us when we're talking about ionizing, right? What does that mean for energy levels? So I'll let you think about this for a second. I'll write out our relevant equations, right? We have our energy of our photon. And so the other thing that I kind of want to point out while we're looking at these equations, and I'll show the book. And so it's kind of confusing, and honestly, I always get confused too. And so, right, the difference in the signs and like what it's trying to tell you, right? Oh, what's higher, what's not. So basically, right, so this one is the energy of a photon emitted, right? So it's saying it's relaxing back down. So that's why it has, okay, your initial has to be greater than your final. And then this one is showing, right, energy absorbed. But the thing is, this is the same, right? Your magnitude is the same. And so the only thing that you can kind of mess up is the sign, right? So if you flip this order and get confused, because honestly, I get confused too, the only thing that'll happen is you'll get a negative energy. And then, right, you know that, well, if you're putting in energy, right, it has to be positive. If you're talking about energy release, it's negative. So that's where you can just check yourself with the sign sanity, right? But it's saying the same thing. It's measuring that same amount, right? Whether it's going in and we're promoting it or whether it's relaxing.
What's the name of that equation?
I don't know. The energy equation. Yeah, so this is, right, one relevant equation. And then, of course, the other form is, right, the Rydberg-Balmer equation, which all this does, and then your book kind of even makes it more specific, but it's talking about the visible transition. So we can still use this, though, for any transition, right? Doesn't matter. But again, if you end up with a negative wavelength, oops, just flip the sign, right? You obviously know you can't have a negative wavelength, so you just know you did something backwards there with the numbers.
And the 1.097 plus 10 to the 7, that's a constant, right?
Yeah, so this would just come back, right, if we were to take this equation and then convert the energy, right, back to wavelength. So with like our other relationship, right?
Okay.
So any of these, so if we could probably derive it, it's probably just like a constant like this and multiplied by our factor of energy.
But it doesn't, it's not like someone's constant.
Yeah,
It's just a constant.
yeah, it's just like a factor, yeah. It's just the factor that comes out from going from energy to wavelength. So yeah, these are your main equations there. So what do we need? So we'll go back to the problem now. What is it asking? Oh, yeah.
Just a quick question, are those, like, is that like page on Blackboard by chance?
I just posted it. Yeah, it should be. I don't know if it's quite under the week 5.
Thank you.
It is fresh. And so as you think about it, so question in the chat, does ionize mean that we are exciting the hydrogen? Yes, right, but we're exciting it so much, so what does ionize mean? Where is that electron going?
Away, like it's completely.
Yeah, so it's, right, we gave it so much energy, we excited it, it flew off. So what does that mean? We try to translate it. Anybody figure out the math? So what's the trick then? What's our, basically what am I asking is, what's our NF when it's ionized? If it's gone, where is it mathematically? Infinity, exactly, right? So now it's gone out to infinity, right? So how this works, okay, we're calculating higher and higher and higher energy levels, but then each one, so remember as we get to the outer ones, they're getting closer and closer together, right, out at the edges. So yes, this one is essentially out to infinity, and so now using our energy equation, so we can plug this in, and okay, we... Because, I mean, that's infinity, right? It's gone out to n infinity energy levels, meaning it flew off, right? It left the hydrogen. Yeah, because that's what ionization means, right? That it just literally, the electron's gone. Well, in our cases, we're only looking at hydrogen, so this equation is only meant for hydrogen or hydrogen-like elements. Otherwise, you just put it over a factor, but we're just not that relevant for us, so we're just focusing on hydrogen. But yeah, so then we said ground state, so n equals 1. So now we get that, and then obviously this essentially goes to 0. So we get that the energy needed to eject our electron is 2.18 times 10 to the negative 18 joules there. All right. Questions on that one? Does that make sense? Yeah, so then anytime something's ionized, you can just plug infinity in for the calculation, and that would...
That difference from an excited atom where the electron bumps up a level.
Yeah, right, so then if it bumps up a level in a problem, it would be specified, right? Like we're looking at the transition from 3 to 2 or whatever, and then calculating that.
What does N represent again? It's
The energy levels, so like your principal energy levels. And then remember, right, they just keep going out and out and out, like to infinity, right, like theoretically. And then that's where we say, okay, well, infinity, though, is where it has left the atom, though. Yeah, so yeah, thinking of like just going back to the principle like Bohr model. So, right, n equals 1, 2 electrons, n equals 2, holds 8, et cetera, et cetera. But then n equals infinity. Yeah, so that's the equivalent to leaving. And so, again, conventions, so it depends on what we're talking about. So I'm saying energy needs to be input to eject it, so that's why I have a positive sign. All right, now let's look at this next one. So going back to our quantum numbers. So good review. So see if you can figure out, so what subshell is it referring to? What orbitals? So L. All right, let's do A. So n equals 2, L equals 1. What orbital is that? So 2p, we all agree. So yes, 2p. And this is, again, why I like to have the periodic table label. So L equals 1. Okay, so it has to be a p block, so 2p, right? Could be any of these elements. What about n equals 4, L equals 2? What's that? So 4D. You like that? And so again, that's why I like labeling. So it's somewhere here on this row. And then n equals 6, L equals 0. What's that? 6s. So 6s. So either cesium or barium. Excellent. Questions about that one? All right, let's do another one of these. So try this one. So the threshold frequency of gold metal is 1.2 times 10 to the 15th hertz. So will ultraviolet radiation of wavelength of 200 nanometers eject electrons from the surface?
Could you zoom in on that?
Sorry?
This one have to be meters as well?
Yeah. So what have we gotten so far? What equations could we use? Yeah.
So I'm trying to use the E equals Planck constant times the speed of light over lambda. And I rearranged it so that it's Planck's constant times the speed of light over the energy level, it's 200 nanometers, should equal the wavelength.
Yeah, I wouldn't use energy though, because we don't have, right, we just have frequency, we have our threshold frequency, and we have wavelength of 1. So I think there's a more direct approach. Yeah, Ben?
I don't know if this is right, would it just be, frequency times, the wavelength?
Yeah, so you're talking about frequency times the wavelength equals C. Yeah, so this is what I would use, right? So use this equation so we can calculate, well, what is even the frequency of what we're starting with, right, of this UV radiation. And so again, now we can plug this in. So 3 times 10 to the 8th meters per second. So we're trying to solve for frequency. And of course, convert this to meters. Let our units work out. So let's see what we get.
So would it be C divided by, the frequency?
Yeah,
Okay.
and so you could also see that, right? So then you could do, let's rearrange. You can also see, right, dimensional analysis works out. So divided by, just wrote it. So meters cancel, so there's our units of hertz coming back out. And then, okay, calculator spits out 1.5 times 10 to the 15th. So hertz or inverse seconds. And so yes, do we think this will work? Does it seem appropriate? So yes, right, it's higher, it's than our threshold frequency, so we have 1.2, and we're at 1.5, so yes, that would be appropriate, yeah.
So all we would need to see is that the, answer that we come out with is higher than the threshold frequency?
Yeah, so remember, right, frequency is how many times it's passing by a certain point, so as long as it's higher than that, right, it has enough energy. So higher frequency, higher energy, yeah.
So the V0 is representing that it's just at a ground state?
Sorry, the 0, like for,
Like, because it has a subscript of 0 right there on the equation, is that just representing?
oh, yeah, this is just like threshold yeah, like minimum. Any other questions on this one? All right, let's look at some other ones. Let's do, sorry, I'm trying to figure out what electron configuration I want to do. Let's see, let's at least do, well, actually I want to change one of these. Let's do iridium instead. And let's try iron. Might as well do nitrogen. So try nitrogen, iron, and then let's do iridium. And so draw orbital diagrams, but also write out the electron configuration.
For the previous for the previous question, the answer that you wrote there, is that 15, 10 to the 15?
Yeah.
Do you want us to do all of those or just?
Yeah, let's just do the highlighted ones. So nitrogen, iron, and iridium.
Is it orbital diagram just the arrows?
Yeah, so just sketching out like the little diagrams.
I like that periodic table where it has.
Yep, they show me.
I think it's right.
Where it's like fit in there. Yeah. We ready to go over? Okay, let's start with nitrogen. So what's nitrogen's electron configuration? Someone can yell it out.
I put helium, and then 2s2 and 2p3.
So excellent, so everybody agree with that? And so right now we can just draw out our orbital diagram. And so right, again, just think about any questions that could be asked as well, like how many unpaired electrons does nitrogen have? So that's where you need to draw this out. Okay, 1, 2, 3. So that's how you can determine that. All right, now let's look at iron. So who wants to give me electron configuration? Yeah, go for it.
It's gonna be argon in the brackets, and then, 4s2, 4p6,
Oh, not 4p6.
3p6.
But that's the D block, right?
Oh, is it?
Yeah, so make sure, right, label it. So this middle part starts our D. So 1, 2, 3, 4, 5, 6. So 3d6. So excellent. And so now we want to draw our orbital diagram. So we can draw out our D orbitals. So 5 of them. 1, 2, 3, 4, 5. And our 4s. So I'm putting 2 in the S, and then 1, 2, 3, 4, 5, 6. And so now we could say, right, we would probably predict from this diagram that iron would have 4 unpaired electrons. Question? Since the d orbital, remember, has 10 sublevels in it, or 5 sublevels in it, so write 5 d orbitals. So 10 total electrons. Yeah, there's 5 of them.
And the d orbital has 3, right?
Yeah. And remember, you can always take how many across there are and divide by 2, right? That gives you how many sublevels. So obviously the S just has the 1 sublevel, right? The P is 6 across, so that's 3 P's then. The D, right, 10 across, so 5 d orbitals. And then remember for this F block that we have to count it starting here so that we get 14. So remember there's 14 in the F. And then of course, right, divide by 2, so 7 F orbitals.
Is that a theoretical fifth block without 18?
Uh,
You have 1, 3, 5, and then 7.
yeah, so 7, then it'd be 9. Yeah,
18,
yeah. But let's focus on this. All right, so that was that.
Wait, where did the lanthanide
So remember lanthanides, so I always put lanthanum and I labeled it on this periodic table. So remember when you fill it in, so lanthanum I always say starts 5d1, and then cerium starts 4f1. So right, cerium's electron configuration will include a 5d1 and then 4f1. And then right, then you just fill up the rest of the F, and then you go back and just start filling up the D's again, right? So we're just continuing with our 5D, right, after filling up the F block. And then, so let's do iridium's electron configuration. All right, so who wants to give me, I don't know why I wrote iridium. Yeah.
I started with xenon, and then 6s2, 4f14, and then 5p6.
That one's good. 5D7. So is that what everybody got? And so, right, make sure that you didn't forget the 4F14. So that happened to a lot of people on the quiz, which we'll talk about more. Try not to talk about it, though, because some people haven't taken the quiz. So yeah, don't forget your 4F, and then going back and filling your Ds. So 1, 2, 3, 4, 5, 6, 7. So that looks good. Questions on that one? Yeah, Trinity. Yeah, well,
Lanthanum starts like the D orbital for like the fifth level, but then after that it's 4F for the rest of the lanthanums. Oh, okay.
yeah. So lanthanum should really, I think, be with the D block, but I think there are other articles. I didn't research the article to look at the argument why these are in the F block versus those. But electron configuration speaking, the way it falls is, yeah, you fill up lanthanum with the 5D1, and then you fill the F block, so even though there's one electron stuck in the 5D, and then you go back and fill the rest of that 5D. Yeah.
So to kind of expand more on that lanthanide series, I'm noticing that lanthanum and cesium, there's the 5D1, and then cesium has 5D1 4F1.
Right.
But then,
So are you talking about cerium?
yeah, cerium.
Yeah, so cerium, yeah, correct. It's 5D1, 4F1, yeah.
And then as it continues down, that 5D1, it drops off and it goes to 6S2, 4F3.
Yeah, so that's goes back to kind of like not beyond the scope of this course, but like I might ask you that on an exam. So all that is right, again, the orbitals are so close in energy that sometimes it's more favorable to move it from the 5D1 to just start filling out, right, those 4Fs. Especially if you could fill all 7 F orbitals, then it's definitely going to want to take an electron from like the 5D. So that's where those like discrepancies start to occur. So yeah, on an exam though, I would accept either answer, right? So if I had asked you to do the electron configuration of sodium, right, then I would accept both 5D1, 4F2. Or if you just assumed, hey, I think it's just going to go into the F, then I would also accept, right, 4F3, and then obviously the beginning part. So does that make sense? As long as, so the most important thing, and this is where people got in trouble on their quiz, is that the total number, right, adds up. So you want to make sure that whatever your xenon is plus all these electrons add up to the correct number. Because then it'll be a little flexible, right, if you put, you know, an electron in the 5D versus the 4F, right, that things do get weird, you know, realistically speaking, but we're just trying to do our best kind of theoretically. Does that make sense?
So when you're listing out the 6S2, you put, or when between the F shell and the D shell, you would list the F shell first and then go into the D shell because that's the more outer shell.
Yeah, well, it also goes back to like reactivity. So in this case, like this 4F14 is essentially like a core electron. Like iridium's not pulling from these F orbitals. It's going to be pulling from the S and the D, is how it behaves. But. Right, so we all clear on that? So right, again, that's why there are like discrepancies as we check it with our electron configuration, right? But so there are expected patterns. So it kind of jumps around, right? And then notice with this next element, element 64, so once that F orbital does have 7, right? So you have 1 electron in each of those 7. Oh, now it goes back and sticks another one in the 5D, right? So again, it's just all about what's more energetically favorable. All right, and then so for this one, we can draw out our orbitals. And so the most important are going to be the Ds. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. 6, 7, so we can tell we have 3 unpaired electrons with iridium. We can draw out the 4F14, but right, that's just not as relevant since they're all kind of paired, so not that exciting. 1, 2, 3, 4, 5, 6, 7. And 6s2. And those, again, should be really close together. Feeling better about electron configuration? Let's practice a few, at least, of these charged ones. And so let's do an F block one just for fun to look at it. And let's see, what else should we try? Let's look at chromium, because that will also be fun. And
Maybe like Lewis dot structures.
just electron configuration. And then you could write out orbitals. Yeah.
But actually, what I'm asking about is how does the removal of the electron affect the electron configuration?
So what I would do is I'd probably like start with a neutral, and then, right, well, if it has 2 plus, then you know you're removing 2 electrons, so then you got to kick off, right, 2 electrons from your electron configuration. And so hopefully with the electron configuration, again, if you start with a neutral, then you'll see, okay, these are probably the ones getting kicked out, and then you can write your new electron configuration.
You'll always lose and gain from its valence electrons, right?
Yeah.
Makes sense.
So it would add up to more than what
Well,
the neutral state is, or?
this one will be less because it's 2 plus, right?
Yeah,
So you'll
but
have,
I mean, sorry, I meant like if for like the opposite side for adding an electron, then it would be more than.
yeah, yep. So yeah, if we had, well, yeah, maybe we should do sulfur too as well, just so we can see what adding an electron looks like. And that's sulfur 1 minus, which is strange. Wouldn't expect that. We ready for calcium's, or let's, calcium 2 plus electron configuration? Yeah, what do you get?
We got 3s2 and I think 3p6.
So you want to start with neon? So neon, and then 3s2, 3p6. So that looks good, right? And so this is essentially the electron configuration, though, of argon, right? And that makes sense. So calcium 2 plus lost 2 electrons. You could also have started with the neutral. So calcium neutral is argon 4s2. So then we see, okay, well, we're losing these 2 outermost electrons. Yeah, and you could also write argon, but it might be better to explicitly show, yes, what the core electrons of argon are.
Do the elements mimic the elements that they're charged to? Like in this case, it matches up with argon in terms of its electron configuration. So you're sharing properties of argon that's in that state.
No, it's just like the electron configuration.
Is it stable? Because now it has the electron configuration of argon, which is a noble gas.
Yeah, so then it's more stable. So then, right, this is why you find a lot of like calcium compounds out there, right? Calcium carbonates, calcium oxides, right? You can do field exploration, and there's a bunch of calcium, mainly calcium carbonates, but yeah. So that's kind of, right, it's a stable form, but obviously, again, right, alkaline earth metals, so that's why they're in that 2+ state. All right, let's see how our sulfur went. So what do we get for the electron configuration? And again, it is sulfur -1, so that is a little odd. So what's the electron configuration? Ben, you want to go for it?
Yeah, I did neon, and then 3s2 and 3p5.
3p5. So I see nods for that. So excellent. So we just had to add another electron. Again, if you have to think about the sulfur neutral, right? Obviously that's neon, 3s2, 3p4. And so adding that 1 electron brought us to 3p5. All right, let's try, what do we get for chromium? Chromium 2+ here. Sky, did you want to do that one?
Sure. So argon brackets, 4s2, and 3d4, but it's +2, so 3d2.
Yep, so 3d2, so 1, 2. So let's just put that, so chromium, again, the neutral. So argon, 4s2, 3d4. And then, so this one, this would be okay, right, for an electron configuration. But if you look at the neutral, you might suspect that it might pull those 2 electrons out from the s. So probably another way to write it would be just argon and then 3d4. So it depends, right? So again, we can look at the neutral. So the neutral is 4s2, 3d4, right? And so just mathematically, you could just remove 2 from the d's. But then if you kind of start thinking more chemically, it's going to pull from the s, actually. It's more favorable, and that's how they behave, because those little s orbitals are like together, so then it's gonna like lose that first. Not because it's in the first shell. It's just has to deal with like where those electrons are paired. So that's where you start getting like common oxidation states, right? So like basically either chromium's going to lose 2 electrons or it likes to lose 6 electrons. So you see a lot of chromium 6 compounds too.
Would that also be related to like the ionization of the element as well?
Yeah. So we'll kind of talk. Yeah, we'll talk about ionization energies, but exactly, right? You have to be thinking about those orbitals and how they can both shift around and like what they can lose, what can happen.
How come
Sorry, what do you mean the first one? Sorry, are you asking about this one?
Oh, yeah, Hopper doesn't lose the 3s2 for, calcium +2.
I guess, so calcium, so right, we have to go back and think about the neutral with all of these, right? So going back to calcium, calcium had the 4s2 to lose, right? So that's why I lost that, and that is the outermost valence electrons. Yeah, what you actually find, and so basically, like your numbers here, 3, 4, 5, 6, that's like what their D counts are, is how inorganic chemists treat them. So they essentially ignore that they're like in the S because they behave so much like Ds, but that's for third quarter of this class more, but we can already. Huh. Yeah, so mathematically, on a test, I would accept either answer, right? So this is just what we expect mathematically. I'm telling you this is how they behave, but again, that deeper understanding kind of comes as we see how they tend to react. And again, that's why they have these common oxidation states. All right, and then let's try our F block one over here. So gadolinium.
I have two different things for this one. The first one I have is 6s2, 5d1, and 4f4. Oh, I'm sorry, xenon first.
So xenon, and then so you have
6s2,
6s2.
5d1, and 4f4. My question would be, would that 1 in the D go up, so can you just 6s2, 4f5?
That would probably be a good assumption. It's hard to know.
Okay.
But yeah, so I like this answer. So did we all get to this answer? Okay, so I see a lot of nods. I'll write just the neutral really quick. Oh, right, so of course, if we're starting with our neutral, so that gives us xenon, 6s2, 5d1, 4f7. And so that's probably, what we predict both, again, just like doing it our kind of mathematical way, but then also kind of predicting like, yes, right, if we have one electron in each F, then probably makes sense that it has the next one in the D. But then like Autumn's point was, well, looking at the charge one, okay, this is a correct answer, again, mathematically. But then, yeah, right, it will probably pull from the D first, right? So then an alternative answer, if I can do my math correctly, so 4f5 then, right? So then you end up 6s2, 4f5. The main point being, do we have the correct total number of electrons, right? So this is a good answer, and then this would also be acceptable if you wanted to move that electron over from the D to the F. Does that make sense? And that's probably, again, how it's pulling. So that's where you go back to, right, looking at the common oxidation states, how it reacts. All right, this is probably a good point for a break, and then we'll talk about ionization energies and your quiz and go over those problems. Then I'll try to hand back some more stuff. Yeah. I wouldn't mark you wrong on that. So that would be another permutation. So if you pull those three, which is actually not thinking about it, probably a better thing of what happened. So yeah, that would also be correct. Yeah, let me probably write that. Hey.
Sorry, I didn't comment earlier to confirm my daily existence. By the time I did get here, classes started in session. I didn't want to disturb. So,
I mean, you can always run in.
I have a question on homework.
Okay.
So, for these three, I was able to find that because there was a table in the textbook, but I couldn't figure out for potassium at all.
Well, you shouldn't be going off a table, Rick. You should be going off of trends and all our things that we've talked about. So then, sodium versus potassium. So which one, what happens to the ionization energies as we go down? Think about reactivity too. Who's more reactive?
I'm not sure.
Remember, they get more reactive as you go down.
Oh, okay.
So then what does that say about our ionization energy?
It's more reactive and it takes less energy
Mhm.
for that reaction to occur.
Yeah, so then who has the larger one, potassium or sodium?
Okay. Larger versus ionization, so that would be sodium?
Yeah,
Okay. Because it takes more energy for that to happen.
yeah.
Got it. Okay. Thank you. That's all I've got for now. I'm still working on it. And I did want to talk to you about midterm. Do you have my letter of accommodation?
I do, but we should talk about it.
Okay.
I have to pull up everybody's letter. I don't know.
Oh, I want to do it.
Okay.
So, because it should say that I have double time for test.
Okay. You might have to test in the testing center. I don't know. I have to look privately who has accommodations. I can't have you looking.
All right, got it. Can we talk about it after class? Then?
Yeah.
All right.
So about, on the quiz, the lowest first ionization energy.
Oh, I'm gonna go over that.
You are? Okay.
Yeah.
Cool. Thank you. I finally started to figure out the electron configuration, which is great, but I still don't understand the noble gas trick. I'm not sure how to tell which one to pick and what the...
I mean, you could just do it like numerically is what I always tell people, like especially when you get over here. So, okay, we're looking at like cerium, for instance. Okay, it's 58, so we have to start with something less than. So then I would pick xenon and then start there.
Oh, right on.
Yeah, so that's where it's like, just go by the numbers, and then that'll help.
Yeah, is it for determining like which shell you start on? Do you just like count? Is there a trick for?
Well, then you just start going, right? So then, yeah, so if you're, again, doing cerium, you start at xenon, and then we just fill across how we expect, right? 6s2, then 5d1, 4f14, 5d2, d4. Yeah, so you're always just filling in, like, theoretical order. Yeah, so like we're seeing, there's, like, little discrepancies, but we're mainly just filling in mathematical order of the energy levels, what we expect.
Okay.
Because what this is reflecting is essentially, right, the mathematical ordering, that the 1s is the lowest, and then you have the 2s, right, the 2p, et cetera, et cetera. But then, again, the thing is they get closer and closer to each other in energy, so then you get weirder and weirder stuff, basically.
Okay, cool. I think about it. Thank you.
So you said the second half of the test is the written portion, and that's open book.
Yeah.
I do not have my book yet. It's on its way, but it's not going to be here after this week. So, and I've checked the grants pass and this library and Trio, and no one has it. Because I've just been using the chapters that you have posted.
Yeah.
Is there any resources you might have?
I mean, other than directing you to like OpenStax textbooks.
Is that, And that would be like on my computer.
Yeah,
Is that acceptable during the test?
yeah,
Okay,
yeah.
okay.
I mean, the textbook's also online. You could probably find a PDF of it.
Okay, as long as I can do that, then yeah, I'll figure it out. Thank you.
And then once something actually happens
So I had another question here. I think it's a half point off this one, but I was confused why. It just says half.
Yeah, I'll go over that.
Okay. Cool, thank you.
Sorry.
we're going over ionization levels?
Yeah.
Thank you.
Yeah, I'm gonna go over the quiz.
I wanted to ask real quick, do we need to know like the official like names of like all the orbitals, or it's just
nah.
like just for our knowledge, I guess?
Yeah, so right now you just need to know that there are 5 of them. But
Okay.
yeah, we don't care what they are. Later on you'll care, but
Yeah. Okay.
not today.
I was just wondering if you had the extra copies here with you, or if they were like.
See what I have. You'll have to make up the flame test. I think that's it.
Yeah.
So how do we figure out what region of the electromagnetic spectrum this belongs to?
Oh, so then you have to refer to a chart.
A chart? Is that in
Yeah.
the textbook?
Yeah, there should be one in the textbook. No, that's the unit. Yeah,
Oh.
so the unit that you get out.
So this would be. Ignore this. I was trying to figure that out.
Yeah. Yeah.
Okay.
Has it already been 10 minutes?
I'm not.
All right, did we all make it back from break? So I just wanted to go back to this last problem that we were just looking at, because I realized a better alternative answer, or someone pointed it out to me actually. So right, again, if we're thinking 3 plus, so really where it will probably pull the electron from is the S and the D. So yeah, if you had written the xenon 4F7 as your answer, right, that would also be appropriate. So again, the main thing is that the total number of electrons is correct, so write all these permutations. So if this answer, this one, and this one, I would all consider correct for our purposes. But again, probably thinking of how it behaves, it's pulling from the 6s2 and the 5d1. All right, let's try this problem. So a space probe identifies a new element in a sample collected. Successive ionization energies in attijoules are shown. So to what family of the periodic table does this new element probably belong to? So take a look at that. Question?
Is all of this on Blackboard, like this page and everything?
Yeah, it should be.
Thank you.
all right, so what do we think for this one? Where's the big jump?
I think it's either row 1 or row 2 element because there's a jump between 2 and 3. And then between 3 and 4, there's actually a small drop off, which indicates that there's an unpaired electron on the 4th energy level.
So I would, yeah, look at this large gap here. So then what family then does it belong to? So how many valence electrons, right, is this showing? So 2, so it's some sort of, right, 2 plus ion. So can we tell that? So that's kind of the first question with this ionization energies, right, is like, what is it showing us? And so yes, right, we said each subsequent ionization energy is always larger, so that is true. But again, you're trying to figure out where that jump is. So this is where the jump is. So there's a much bigger gap, right? So this is like a 3 difference. This is only 0.5, and then, right, these are all like 1, 1, 1 roughly. And so that's where you have to identify, okay, this is our jump here. So then probably, right, alkaline earth or something. So let's do another one of those. So identify this element. So what element might this be, or what, how many valence electrons do you think this element might have? Where's the jump between? The 5th and the 6th. So don't let those decimals confuse you. So they were really trying to throw y'all off with this one. So yes, right, we go from 6,000 to 21,000. So that's quite a jump. So yes, I like that. So right here's our jump. 5 valence electrons. So who could this be? Not chlorine, because chlorine has 7, but who has 5 valence electrons? Yeah, it could be, right, nitrogen maybe, phosphorus. Vanadium's more transition metal, so probably. Yeah, for these, right, stick to main groups, and yeah, I mean, you're probably not like wrong in guessing like vanadium, but we're trying to stick to like main groups so we don't get too confusing because there are too many exceptions with deep
I have a
things.
clarifying question. So where the jump is, that's where how where you start to pull out of the core. right?
Exactly, yeah.
Okay. So it's 5 because it jumped between 5 and 6, meaning it's nitrogen because it has 2s2, 3p3.
Yeah,
And those are your two valences.
exactly.
My other question is, why is S considered a valence electron? If
Oh.
it's not a core?
It's just like where it pulls, because it's like the outermost ones.
Oh, because it goes 3, so it goes 3p, 2s, so those are two outer ones, right?
Yeah, well, you have, right, your 3p, 3s.
Or 3s, excuse me.
Yeah, so, right, it's pulling, so
Down.
depending which one it is, right, if it's nitrogen, it's pulling from the 2p and then the 2s. This is probably something else since it has, right, more electrons. So nitrogen only has 7 electrons total. So this is probably phosphorus or higher. But yeah, right, essentially it's pulling, now we can draw out our electrons. So it's pulling out, right, our 5 valence electrons, and then now that jump as it goes into that core, right, that's completely filled.
Okay.
We could, you know, go on and on.
So for that jump to the, because, so that jump from the 5th to the 6th, going into the core of it, and if it's considered nitrogen, then that core would be helium?
Yeah, yeah, so then we'd be down in the helium core.
So on the previous one, can you go back to that? So that jump from I2 to I3, that core would also be helium, and then that's how you got the alkaline, is because it's just one, and then you would have two. Okay.
Yeah, so you have, right, the jumps from 2 to 3, so you know you have 2 valence electrons. And then, yeah, so it's any alkaline earth. All right, so if you haven't taken the quiz, I may ask you to step outside, because I want to go over the quiz, but I don't want to give it all away. So yeah, if you haven't taken the quiz and you're in here, if you could step out and then we'll take, well, do you want to take the quiz? Who needs to take the quiz? We should just have you take the quiz. All right, who in here needs to take the quiz? You want to do it? Let's just do it now, and then you can watch the review after and finish it. Anybody else need to take last week's quiz? Yeah, just step outside, take the quiz. All right, anybody else last call? Good. I'll wait for them to exit. All right. Now let's go over the quiz. Ah. Oh, that's not even the right quiz. Okay, whatever. So let's go over number 3. So it says, so which has the highest ionization energy? So highest, and this said first ionization energy. And so the answers were selenium, sulfur, chlorine, and bromine. And so for this one was just general periodic trends. So again, right, we'll go over this again right now. But right, the idea is, well, in general, right, as you go across, you have increasing ionization energy. And so, right, that goes back to, again, our effective nuclear charge. So as we go across, right, and we're filling in that same energy level that's at the same distance away, then that, of course, creates a greater pull. So then that's going to take more energy to eject it. And so then what was the answer for this one? So chlorine, right? And again, this is all just periodic trends for this one. So we were comparing, right, selenium, sulfur, chlorine, and bromine. And so chlorine was kind of the uppermost right here. So that's going to, again, have a high ionization energy. That those the 3p, right, is closer to the nucleus compared to, right, the 4p here of bromine. Then it has an extra electron, right, compared to sulfur. So again, another electron in that effective nuclear charge. All right, so that was 3. And then we'll go back to 6 in a second. And then, so let's look at 7. So many people still got this right, but it was a mixed bag, so I want to talk about it. So this was which of these atoms had the lowest first ionization. And so this was tricky. So we had boron, aluminum, magnesium, and beryllium. And so, again, the trick of this is we have to think about all our orbitals in addition to, right, our periodic trends. And so kind of what we have to think about is, right, again, even though we said, okay, increasing ionization energy as we go across, we have to think about what happens, right, from here to here. So we're going from an S to a P, and that P is slightly higher in energy. And so it's happy to get rid of it then. And so kind of, so now we're looking, oops, oh gosh, not what I wanted to do. So kind of the choices that we had to come down to, I think, are magnesium versus aluminum, right? So did people kind of get to that conclusion at least? So we're going for lowest. And so again, right, we're comparing beryllium, boron, aluminum, magnesium. Okay, lower. So we're looking for something with that energy level that's further out. Yeah.
Is there something else on the periodic table? Like, I don't think it would be atomic weight or something like that, but that tells us that jumping from the S to the P means, or the P is going to be higher energy. Like, is there another piece of the puzzle that basically tells us that jump from S to P, the P is going to have higher?
It's just like going back to the ordering of the electrons, right? So as we fill them in, so we know, okay, well, the 2p is just a little bit higher. Yeah. And so that is tricky. And then again, right, that's why we're taking this deeper approach, right, with orbitals. So that distinguishes like our college level chemistry. And so now I would say, okay, we've kind of come down to these two choices. So trend-wise, right, it would suggest aluminum. But again, we have to think about, so our 3p, so we have 1 electron in that 3p for aluminum. And of course, our 3s, so 2 in there, versus our magnesium. So, right, doesn't have any in the 3p. So they're both in that 3s, which is, again, slightly lower in energy, which means it's closer to the nucleus, right? So that's also what you're thinking about, is distance to the nucleus. So closer to nucleus. And so, again, you have to think about, okay, we actually added another layer, right? Even though it's still in the same principal quantum number, but yes, right, it's slightly further out. It's a p orbital. So yes, it is technically a little bit further out, So aluminum has a lower first ionization energy since our p orbital is slightly further away from our s. So that was tricky. So aluminum is the lowest. And so let's go back to 6 now, because again, 6 was another tricky one, and that was one of those that we had discussed in class. And so, right, kind of the conundrum is that nitrogen and oxygen, right, don't follow the trend. So again, just the, right, general trend. And so again, that's where we have to take the orbital diagram approach to really understand why that it doesn't follow the trend. And so I was looking for some sort of orbital diagram picture. So you have nitrogen with our 2p here and our 2s. So nitrogen, right, versus oxygen. And so we had to remember, right, that this is already unfavorable. So, right, there's already energy lost or paid to have them in that same suborbital. And so that's why it takes less energy to eject this electron since, right, it's essentially getting that energy back out now. And so that's why there is a slight drop from nitrogen to oxygen, even though, right, again, following general trends, what we expect from just our effective nuclear charge is that oxygen would have a higher one. But then we actually have to take into account this energy pairing. Yeah.
Is that true of that whole family? So sulfur versus phosphorus and arsenic versus selenium?
Yeah.
And so on and so
Yeah,
forth?
exactly. So yeah, take that trend and then, so that's all the way down. So all those would have that same sort of idea, right, where they're paired, so that always pays that energy price. So that energy price argument, you know, can come into play. Yeah, let's start with Ben and then.
It's not, this is a little bit more, I guess, related to the last question that we went over. So, when we're thinking about lower ionization energy, would the same be true if, like, we were dealing with scandium, which isn't, like at the start of the p orbital, would that also be lower ionization energy, or is it purely just because there's a jump from the 2s to 2p?
Yeah, so you're saying calcium to scandium?
Yeah.
Yeah, I would predict that. I would have to look up the actual numbers since, so the problem is, right, the d orbitals on that trend, they start to get even funkier and just kind of bottom out on the ionization energies. But you've got kind of the right idea there, so. But yeah, for ionization energies, I probably won't do anything on the transition metals just because, again, it gets too weird because those d orbitals can quickly become not degenerate and then, yeah. Oh yeah, Jonathan, sorry.
So it has lower energy. Oh, I can see right here it has lower energy than oxygen than nitrogen.
Yeah, so the oxygen has lower ionization slightly. Yeah, so you have to think about, so what it took, right? So before you even think about ionization, it just like sticking that electron into this suborbital was not favorable. So they were pairing an energy price to like force them into that orbital, right? To be in opposite spin states. So that's what that's saying. But then it's like, okay, if we eject that electron out, we no longer have to kind of force them together. So we get that energy back. So then that kind of balances out, right, the energy to eject it. Yeah. On Thursday.
Can you say that one more time about the oxygen and so the electrons in that?
Yeah, so like, yeah, just imagine, so imagine we're at nitrogen, and then, okay, what does it take to stick that extra electron into that p orbital, right? And so what's happening is doesn't want to be there, right? So it's like you have to force it to be in that orbital and basically have those opposite spins. Yeah, it's like it's a little repulsive, right? Since they have opposite spins, so yeah, there's like a little bit of repulsive force there. So there's a little bit of energy there to have them in that same orbital. Yeah.
And then, so for on the question or on the paper, when you say use the atomic orbital diagrams in your explanation, that's kind of what you were looking for?
Yeah, so I was looking for this, and then some sort of like statement about energy price being paid or something like that, that this is not favorable to do. So we've already lost energy there. So therefore, right, when we unpair them and by ejecting one, it's a little bit lower energy compared to nitrogen.
So to rephrase that, oxygen does have a higher ionization rate, but it, because of the forcing in the p orbital, nitrogen has, is that correct?
So right, oxygen is overall lower, but I think what you're trying to say is like, yes, theoretically, like it would be higher, but then if we take into account that pairing energy, it makes it lower essentially. Yeah, because right, what the other energy, because you have to think about what forces you're balancing out. So again, we're thinking about the charge that is created by these 4 electrons being in that same orbital, that same distance away from the nucleus, right? So that's competing, that is stronger, yes. So yes, right, like you were saying. But, okay, we have to take into account that energy price. So yeah, I think you've got it there. Yeah.
Will there be questions about quantum numbers now?
There will definitely be quantum number questions.
So in the book, there's sort of a general periodic trend of ionization energy, which does increase from left to right.
Yes.
But then basically the point is when you jump to another orbital, then there's going to be a lowering.
Right, because right, as you jump to a higher orbital, it's physically further away, yeah.
But then it increases as you add more electrons to that orbital.
Yeah, to that subsequent shell, right, because again, you're thinking about effective charge. Yeah.
Would that only be true for like what you said about energy already being lost and or like there's repulsion? Would that only be true for elements at the start of the orbital, and then as you go down, it probably be more likely that it gets higher? I don't know.
Yeah, so I think I get what you're saying. So like, basically though, when you continue from oxygen to fluorine, like, yes, there's still that repulsive effect, but I guess, right, the effective nuclear charge must be more than that, such
So
that.
it's mainly the elements at the start.
Yeah, so it's mainly of that weirdness, again, like you recognize from 5 to 6, where you have that
Yeah.
breaking of the trend. Yeah.
So every time it gets a new orbital, oh no. I mean, no, this one says that 30, there's a dip in the ionization level from 29 to 30.
Oh, from like copper to zinc? Yeah, so that's why, right, we're not focusing on the transition metals, because then we have to draw out orbitals and make all these arguments. Because essentially any like oddity in the trend can be explained back to orbitals, but we're already getting into it pretty deep, right, with looking at nitrogen and oxygen and those subtleties between beryllium and boron. So yeah, we'll save the d orbital stuff for advanced classes. All right, so then let's look at 8 and figure out what that was asking. So then we have to think back of the definition of our ionization energies. And so remember, right, your first ionization energy, you're starting with your neutral metal and getting your just 1 plus cation. So then second ionization energy, right, you're starting with a charged and then going to metal 2 plus. So right, that's our definition. And so then the question asks, compare the second ionization energies of beryllium and lithium. And so what did we find, and what was the key trick here?
So I put out the orbitals, and I noticed that with lithium, if you were to take two, it would go it would go into its core. With beryllium, it goes deeper, but it's not directly into the core of the, so it would be more, to take the beryllium, the second beryllium, it's still further out from the nucleus than it would be to take the second from the lithium. The lithium is, would go into 2s.
Or the 1s, yeah.
1s, excuse me, 1s. Where beryllium, I believe, only would take out the 2s.
Yep. So that was exactly it. So, you know, you could have written out electron configuration to help your explanation. Not necessary, but yeah, you want to say something like that is, okay, well, right, our first ionization of lithium already takes us to helium. So then, right, you have to kick off another one from helium. Well, that's not going to work too well, right? That's going to be pretty high. And then versus beryllium, so yes, right, it does have 2 electrons, 2 valence electrons, so it will lose those more readily and easily versus lithium. So lithium has the higher second ionization. And then I think that was mainly it. And then that last question, number 9, about the radioactive isotope, I was just trying to get y'all to, again, recognize kind of similar patterns. So if we're looking at strontium, right, well, what's strontium right next to? Yeah, calcium. And you have to think about, right, 2+, because it's going to act more like its family, right, than like rubidium, for instance. And so then looking at calcium, well, what do you know about calcium? What's it essential for? Bones. So exactly, right? So that is all I was looking for. So I try to be generous with that one since that was kind of a question out of left field. I was just trying to see how you would recognize kind of our periodic trends. But yeah, that's kind of what makes things like dangerous, or, you know, again, how you can think about like toxicity of things. It's just like, what is it similar to and how could it potentially swap out in your body, right? So then you can think about, so those strontium ions, so they could replace the calcium in your body. And then, of course, if they're radioactive, well, then that's like direct damage inside of you if you are made of radioactive stuff that's decomposing. So
Strontium is to calcium like carbon monoxide is to oxygen, where carbon monoxide will take its place of oxygen in lead cells, and then slowly fixate you. It'll take place, the strontium, was it? Yes, will take the calcium.
yeah,
And then it's
similarly, yeah.
That's
Yeah,
also-
the better analogy that what you're trying to make is, I would say that's a CO2 versus CS2 analogy. So CO2, obviously, right, you expel that. So the problem with CS2 is, and why it's toxic, is it's heavier, and it actually, I think, binds stronger to the hemoglobin
yeah,
than
let's say
CO2.
CO and versus O2.
Yeah,
Okay.
but, so then
I see
that's
how
what.
that's a better analogy.
Yeah, but that's what makes sulfur CS2 dangerous.
I didn't find that. CS2. Is that?
In a lab, I don't know. My friend accidentally overexposed herself to CS2, so I know firsthand how that works. And it's basically like you get drunk, so she felt like she had a hangover the next day. But it's not fun, and you have to go to the hospital, and they got to measure your oxygen levels. Yeah.
So if, say we do run into a question like number 9 on the exam, are you looking for us to look at comparative elements?
Yeah, so you're probably going to look in, yeah, that family. So thinking back to like Mendeleev, and again, right, having the similar properties and reactivities. So that was what that was trying to get at. And then, oh, last thing I forgot to go over from your quiz is, so everybody got, or a lot of people got slaughtered on the first question. And so the problem, right, so it said nitrogen gas and hydrogen gas. And so what you have to remember is these are your, what are these called again? Diatomics, yes, so they have to be written as N2 and H2. And many people did not do that. So there's no such reagent as N and H, so yeah. Remember your diatomics, that's where they come into play, is, writing equations, stuff like this.
So, oxygen forms ozone to get to the very outside shell of the Earth's atmosphere, O3. Are there any triatomic molecules at standard pressure?
I mean, ozone probably exists at standard pressure too, just in trace amounts, yeah. And then, yeah, if you didn't know ammonia, I would probably be more flexible to that, but most people just didn't do that. And, yeah.
Certain math was NH3 or NH4.
NH3 definitely.
It's 3? Oh, that's what
Yeah.
I wrote down, but I couldn't remember.
Yeah, ammonium
I
is
just kinda thought
NH3.
If nitrogen makes 3 bonds, it makes sense that would have to be NH3. Right? That's right, nitrogen makes 3 bonds? Yeah.
Yeah, so nitrogen does tend to make 3 bonds. Yeah, exactly.
CH4 is methane, right?
Yeah, CH4 is methane. So those are ones you should memorize, these small molecules. Let's see. Any other questions that we should cover?
Are we going to be permitted any notes?
So the first half is closed notes, so I will allow a periodic table and metric conversion sheets, so we didn't practice that, but right, there could be conversions, there could also be just made-up conversions that I give you. But yeah, those would be the only 2 resources allowed on the first part, and then the second half will be free response and open everything, minus your neighbors and Google. All right, any other things that we should cover or go over?
Will there be any questions about the Heisenberg equation? Because I'm still a little unsure about
Oh yeah, there might be Heisenberg equations. So what were you uncertain of?
I'm unsure of what everything, because it's the change in X.
Yeah, so it's saying the uncertainty. So it's like the uncertainty in the position and the uncertainty in the momentum, right, are equal to, I think it's h over 4 pi, right? And so basically the question will say, right, the uncertainty in like the position measurement is blah, so what's the uncertainty?
You don't have to calculate.
Yeah, so it'll give you one of them, and then you'll have to calculate the other one,
Okay.
essentially. So like, yeah, if the uncertainty in the position is blah, what's the uncertainty in the momentum?
And then that's just an algebra problem.
Yeah, and then
Okay.
Trinity, and then.
What do you suggest we study for the next few days? For midterm?
I mean, I would look over your homework. I did open up, like, on week 5, there's like some practice problems that you could look at. They're not like necessarily representative, but just like the concepts, right? Conversions, obviously electron configuration. There's going to be maybe a little bit of naming, quantum numbers, everything that we've talked about then.
Will there be any questions about like abundance?
Oh, yeah, that was one thing that I didn't talk about. So the abundance question. So yes, there will be percent abundance, so let's do that really quick. If I can find a practice problem. Hang on, give me 5 seconds and I have a review somewhere.
And it's abundance by mass, not density for points.
It's a percent abundance, but let's do a problem like you'll have.
Is abundance by time mass?
So gallium has 2 isotopes, and if you need to leave, that's fine. We'll rush this one. So the average atomic mass is 69.723 AMU. And if it has 2 isotopes, so gallium-69 has an atomic mass unit of 68.9255. And gallium-71 has a mass of 70.9247 AMU. What's the percent abundance of each? So I'll let you think about it in the last minute of class, and then I'll give a setup. All right, so then in the interest of time, so you have to set up, right, an algebra problem. I think this was on one of your other quizzes. And so it doesn't matter who you call what, but we can call this one x, and then if we set this one to y, so remember converting to a decimal, so x plus y is 100%, but as a number, right, x plus y equals 1. So make sure you get that. So then we can solve for y, so y is 1 minus x. And then so really the trick is the setup. So then we just multiply it, so right how we would normally multiply each one by their percent abundance, except now we have to calculate it. So plus 1 minus x equals our average. And then all this is algebra, so distribute, blah, 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 and then you should get your answer. All right, so probably stop there since I know people probably have class. If people want me to walk through the algebra, I can. But we do have to migrate to lab.
I was just a little confused with oxygen and nitrogen having sort of flip ionization. So with oxygen, there's the pair,
Yeah.
but nitrogen doesn't. So you're saying that it would be easier to pull one from the pair.
Yeah, because remember, you paid an energy price to pair
Already.
them. Yeah. So I actually kind of like how Madeline was saying it. It's like, even though this has a greater effective nuclear charge, right, because it has 4 electrons in the p versus 3, because we paid that energy price, we're like getting that energy back.
Okay, thank you.
Oh, thank you.
Can we talk after a few minutes since everybody else is?
Yeah, we can chat for a little bit.
Quick question. I think you just explained that here, I'm sorry. Second ionization levels. I'm just a little confused. Like, I can see the difference how lithium would like go down and like indicate, and usually the trend is if it's like the lower it is, the better. But the reason lithium's higher is because it took more to make it lower?
Well, because we're pulling from the core, though. So if it's a lower energy level, remember, it's closer to the core with that effective
Which means
nuclear
it's
charge.
stronger.
Yeah. Yeah.
So, okay.
Yeah.
Thank you.
It was on this one. I don't get why this is correct. I want to like just know what I did wrong on that first.
Yeah, you filled it in like funny. I think you did the D's first and then finished with the F's and made, because your total was correct, which confused me. But you're supposed to fill out the 4F14 first before finishing the D.
That's the confusing part because isn't the 5D the first?
Well, you do 5D1, so you just do 5D1, and then you do 4F14, and then you go back to 5D2. Yeah, it's confusing.
That's the confusing part.
Yeah.
Okay.
But yeah, you at least, I think, had the total
Yeah, I got
number,
everything
so that
else.
helps.
Yeah.
I don't know if there's anything else.
No, that was. Thank you.
Yeah, and Zyward, if you're still here, again, the main explanation is that, so oxygen, right, has these paired electrons, but we said that took energy to pair them. So even though it has the greater effective nuclear charge with 4 electrons versus nitrogen, we're getting energy back from this no longer having to pair them.
Once you remove that electron, you have free electrons, just like the nitrogen, but you have.
Yeah, and they're pretty happy to be like degenerate like that,
Okay. So I've got 3 homework assignments turned in, more to come, and they're the first 8 chapters.
Cool.
Are we going over chapter 6 this week?
We're taking midterm.
Okay, so I don't have to worry about chapter 6, I guess, until next week then. Okay, so I still have chapter 4 or 5 homework. I still have to do the reading questions for chapters 3 through 5. And I still need to do all the labs. I've done the in-person part, but I still need to do all the journal articles, abstracts, everything else that's not part of the procedure itself.
Yeah.
I'm making progress. And I'm hoping that I get done with all of it soon and potentially get ahead. On to the topic of the midterm, because I will say, I don't know if you do have nearly as much time as Dusty was when he did started last fall. When I did the major tests with him, he had me come into that office space with him.
Yeah, I don't think I'll be able to make those same accommodations. I mean, is that part of your accommodation?
Not necessarily, but it was just a convenient way.
Yeah, I mean, that's a lot of time for me to.
It was also.
I have a very packed schedule. Like, I'm teaching more this fall than I have ever taught. Since I have that extra lab and I have more students than ever. So I don't think I can do that for you unless you have like a specific accommodation.
And he did that because there would be times where students in class would ask questions as well, questions that he would be allowed to answer for those exams. And being sent to the testing center gets rid of the ability to ask any questions at all. I'm not sure if that's going to be the same case here or not, whether you're allowing students to ask questions during the exam.
Yeah, I mean, I've never done that for anyone.
Because I will say I've also desperately needed that double time before, especially for all the physics examples. It goes on with one, which I finished within the regular amount of time. Everything else was always going beyond the regular amount of time.
Yeah, well, I mean, you can have that time in the testing center. But I guess, like, because you're asking me to sit with you for 4 hours.
Yeah.
Like, I physically just don't have that. Like,
Dusty was able to pull that off
because he's department chair, so he teaches a half load.
Oh.
So yes, so I'm teaching double. Well, actually, Dusty's teaching another class this quarter, because right now everybody's teaching like extra this fall.
Yeah, I know that this term has been like the most packed it's been in a very long time. I mean,
Yeah.
according to all the staff in the science department that I've worked with. Shoot. Some of the options then are either regular amount of testing time, or being able to ask questions, or have double but no questions at all for clarification. And I know that wording on some of the problems can be confusing as well. Because there have been times where I've misinterpreted questions.
Yeah.
I was thinking maybe, if possible, do it in lab time?
During like another lab time?
Yeah, it was
I mean, that might work.
like on a Friday or whatever. I mean, I know that goes into the other laptop, but I know there's not nearly as many students in there.
Yeah, I mean, you would just have to find yourself a nice quiet place.
And there would be a quiet place nearby for that study area, but,
So then are you gonna start the exam at noon?
at noon on Friday?
Yeah.